So now we're going to talk about an important class of test, and that is the accelerated aging test. Now, if you can design your insulating system well, if you can get rid of unnecessary design conservatism, which means you do not have a large factor of safety, you don't try to play it too safe, then you can reduce the cost, you can reduce the size, and that with the elevated levels that we work with nowadays, that will be of a great importance. And therefore, to this end, we need more scientific methods in the design of the insulation systems. We have to have better ways of predicting how that system will behave over a long period of time, given certain operating conditions, given those operating conditions likely to be violated, what would the system behave like? And the main tool that we have in this objective are the accelerated aging tests. Now, what is the principle behind the accelerated aging test? First thing is we need to make a model of the insulation system. And that doesn't mean that you make a two-scale model of whatever there is. You have to figure out what is it that you want to model, which process do you want to model, and that particular process has to be modeled on the basis of the insulation system. So make a model of the insulation system, subject the model to various levels of higher than normal stresses. These stresses could be electrical, there could also be non-electrical stresses, thermal, mechanical, etc. So you expect a certain normal level of stress. Let's say we are considering temperature. You expect the material to be used at 200 degrees centigrade. In this case, what you will do is, you know that over a very long period of time, the continuous application of 200 degrees centigrade will degrade the material. But it will degrade it very slowly, maybe over a period of 30 years. Now, you cannot wait for 30 years to figure out how the material will behave after 30 years at the time of design. But you still would like to know how it would behave. So what you do is, instead of operating the insulating system at 200 degrees centigrade, you operate at higher levels, maybe 500, maybe 700. Of course, I mean, it can't be any which number. You operate it at a particular elevated, so you stress it more than it is likely to be stressed under normal conditions, which means the deterioration will be speeding up, will be accelerated. This will accelerate the deterioration, and from the accelerated deterioration, you try to estimate what would be the lifetime under normal operating conditions. So first, you make a model of the insulation system, subject the model to various levels of higher than normal stresses. This causes accelerated deterioration. The model fails in much shorter time than it would under normal operating conditions. From these results, you extrapolate these results from high stress to normal operating conditions and try to estimate the real service life of the equipment. So this is the principle behind accelerated aging tests. Now we have to, when we talk about building a model of the system, we have to understand what we are trying to model. Insulation system may fail due to a large number of failure processes. And we've already seen that there are so many breakdown processes, and we were just talking about electrical breakdown. Now, when insulation fails in service, it does not necessarily just electrical breakdown that occurs, but very many other different kinds of breakdown can occur, and even electrical breakdown can be driven by non-electrical forces. So, each failure process, every equipment, every material, every sample fails. And that particular failure can be one of the many different processes that are possible. But each failure process is driven by one or more stresses. So it is possible that when you are performing accelerated aging tests, you're not necessarily performing a single accelerated aging test. You may be doing accelerated aging tests for various kinds of stress that you expect will appear on the insulation. So the system and its constituent parts may be subjected to a large number of accelerated aging tests. So what kind of test would you do? It depends on what is the failure process that you are trying to model. So the whole idea of building a model of the insulation system is decided, is governed by the fact that we are trying to simulate the failure process. We are trying to take a particular failure process and we are trying to accelerate that particular failure process. So many of the accelerated tests developed to model particular failure processes have been standardized by international organizations like IEC and IEEE. Now, there are various kinds of tests. Some of the tests evaluate specific properties. For example, what is the melting temperature? What is the tensile strength? What is the dielectric breakdown strength of insulation systems? These are property tests. These are not accelerated aging tests, but they are actually property tests. We are going to use an extension of these tests in the accelerated aging test. Now, before I go on to the tests themselves or the stresses that would appear, I need to make a distinction between insulated materials and insulated systems. Insulated materials is any dielectric material which is used for electrical insulation in power apparatus. I mean, not in power apparatus, any kind of apparatus. In this course, we are going to talk about power apparatus. Now, an insulating system is not just a single material. It is the entire system comprised of maybe more than one insulating material, also the conductors, because the proximity of the conductors will influence the behavior of the dielectric materials. Also, we have already seen that the property or the behavior of one dielectric material is also influenced by the nature of any adjacent dielectric material. So an insulating system is not just one insulating material. It is composed of one or more insulating materials and the conductors taken together. Many of the aging tests evaluate the insulating material constituents. So we would like to evaluate the constituents too. But having done that, when we are trying to estimate the life of an insulation system, it is not enough to evaluate the individual constituents. We have to The life of an insulation system is determined by the capabilities of the system taken as a whole and not by its individual constituents. So, to evaluate the individual material constituents, you can perform material tests for tensile strength, material tests for electrical breakdown, whatever is relevant. But material tests alone are not sufficient to determine the expected life of a complete insulation system. Okay, so what are the stresses that we are going to take into consideration? In terms of aging, we talk about team stresses. T for thermal, E for electrical, A for ambient, and M for mechanical. So all these four forces together, thermal, electrical, ambient, and mechanical, taken together constitute the team stresses, and we often need to perform accelerated aging for more than one stress, sometimes all of them. There are constant stresses as well as transient stresses. Examples of constant stresses are operating temperature, power frequency voltage, magnetically induced mechanical stresses. Time to failure due to the constant stresses is proportional to the number of hours. So for example, if you apply 200 degrees centigrade for 10 hours, it may not break down, but at 15 hours, it will break down. And when instead of 200 degrees centigrade, you apply 250 or 300, maybe it will break down in a fewer number of hours. So generally, the time to failure due to a constant stresses is considered in terms of the number of operating hours. So lifetime is so many operating hours. That is how you define the lifetime of equipment under constant stresses. But then there are the transient stresses which appear across the system due to lightning or due to switching. For example, motor starting, out of synchronization of generators, lightning strikes, and the time to failure in this case is proportional to the number of transients the insulation experience. So you may have applied the stress for a very long number of hours, but maybe there have been no transient stresses. So in that case, the number of operating hours is not relevant. But let's say within the beginning of operation, you immediately see a large number of transients within the first hour. Then n number of transients will cause breakdown. So there is a way we differentiate the behavior of the material under constant stresses and transient stresses. For constant stresses, the lifetime is given in terms of the number of operational hours this particular temperature or particular voltage can be withstood. Whereas in case of transient stresses, number of strikes, how many such transients can the insulation withstand, will experience and withstand. So that difference is there. Now let us look at these individual stresses. Thermal stresses are the most recognized cause of gradual insulation deterioration and ultimately failure. What happens when you apply very high temperatures? Generally, you have current flowing through the conductors. So again, we are talking about the insulating system. When current flows through the conductor heats up. When the conductor heats up, the insulation around it also heats up. So the temperature of the insulation increases. Not only do you have direct current flow, you can have eddy current circulating, you can have stray load losses in copper conductors. So there will be additional heating. There will be heating. There may also be additional heating not due to direct current, but as I said, due to eddy current or stray currents, which we generally lump in as core losses or windage, etc. But no matter what kind of losses we are taking into account, all these losses may lead to heating. So when the insulation heats up, to a certain extent, there is no problem. But above a threshold temperature, generally certain chemical reactions are initiated, especially for modern insulation. When we talk about modern insulation, we are talking about new glass materials, or we are talking about polymeric materials. So certain chemical reactions begin to occur at elevated temperatures. As long as you are below this temperature, you do not have a problem. There is no aging in the material. But when you cross a certain threshold temperature, at which temperature the reactions are initiated, that is when the degradation begins. And once the degradation begins, the insulation will be able to withstand that degradation for only a certain number of hours. And this is the number of hours that we need to determine. For example, always it's not just electrical failure that we are looking at. We are looking at all kinds of failure. For example, to give you two examples, suppose you have air-cooled machines. In air-cooled machines, you have elevated temperatures and you have the presence of oxygen. Oxidation in air-cooled machines causes the insulation to become material. So there is a change in the mechanical property. When the material becomes brittle, it may fail mechanically, or what might happen is, because of the brittleness, delamination may occur in form wound coil ground wall. So wherever you have the ground wall, you have the tape layers. Between the tape layers, there might be delamination due to unequal material expansion. There will be delamination. If there is delamination, that is equivalent to very infinite thickness gap being formed. Whenever there is a gap, we do know that there is electric stress intensification, and electric stress intensification can cause partial breakdown or partial discharge. We will talk about partial discharges later, but this is an example how thermal stresses can cause problems in a insulation, either through chemical reactions or due to delamination, which in turn leads to electrical failure. So the processes might be quite varied. The life of insulation is given in hours, and generally it is related to temperature T in degree Kelvin by an Arrhenius type of law, L equal to A e to the power B by T, T capital T. This law, or this relationship, is generally valid for relatively high temperatures. Below threshold temperatures, we do not have any kind of relationship, because theoretically speaking, below a certain temperature, when these chemical reactions do not happen, no aging takes place. So the temperature should not at all affect your material. You should be able, that its lifetime should be independent of the number of hours of that temperature being stressed on the material. So this is only for below the threshold temperatures specific to materials, no aging occurs. As you can see, in this case, we are really looking at chemical reactions, because Arrhenius rate law is generally valid for first order chemical reactions. But you should remember that when we are talking about insulation, it is hardly likely that you will have just one reaction in motion. There will be several reactions happening together, and these reactions may also, the byproducts of these reactions may also aid and abet each other. So it's not going to be a very simple process. like a single chemical reaction, but it would be a combination of such processes. As a thumb rule, higher the temperature, shorter is the life expectancy. So if you're going to live dangerously, you're likely to have a lower life expectancy. And for every 10 degrees centigrade rise in constant temperature, there is a decrease of life by 50%. So for every 10 degrees centigrade rise in temperature, in the operating temperature, the insulation is likely to last 50% less. There is a reduction in its lifetime. Then we have thermomechanical stress. Thermomechanical stresses are primarily applicable to large machines. So in a large machine, the machine load may change. Now, depending upon the load, depending upon the current through the conductors, copper conductors, the copper conductors will see elevated temperatures. They will heat up due to I square R losses, and therefore they will heat up and expand. And the thermal coefficient of expansion for the copper conductors will be very high. The insulating materials surrounding that will have low thermal coefficient, and they will remain cooler. So there will be shear stresses between the conductor and the insulation because the conductors are growing more quickly and the insulation is not. As a result, there will be a shear stress between the conductors and the ground wall insulation. As a result of this, after many load cycles, so every time increase and decrease takes place, bonding between the insulation and the conductor may break, and in that debonded region, you may have partial discharges, or they might even be crack development. There is really no simple relationship to relate the thermomechanical stresses with temperature, but it's safe to say that larger the temperature difference, fewer the cycles to failure. So more quickly. So it's like in the desert, the rocks expand during the day, contracts at night. So this continuous expansion and contraction goes on, and as a result, they disintegrate into fine sand. Some similar process can happen in your machine also. So this cycling is a problem. Then we come to electrical stress. Now, power frequency voltage can stress the system in the presence of partial discharges. You apply a power frequency voltage, and if it is within the system voltage, there should not be any problem. You should not have any degradation. But as we know, what really happens is there are often So always we don't have breakdown. Breakdown is a failure indicator. You perform a breakdown test and the material breaks down, of course, a breakdown has occurred. But with aging, we are not always looking at such catastrophic failure. So, for example, when you are performing an aging stress with the stress as voltage, lifetime is measured as the aging time required to puncture insulation. That means the time to break down. So this is easy. This is kind of a pass-fail criterion, which is easy to work with. However, there might be other tests where it is very difficult to define failure. There may not be such kind of catastrophic failure. And in that case, we have to determine what are called failure indicators. For example, if you have thermal aging, the consequence may not be that it actually burns, but there may be a loss in mechanical strength. The material may become more brittle, but there may not be any catastrophic failure. So in that case, we will have to use a diagnostic test over certain intervals of aging. Diagnostic test could be a measure of a particular property. These diagnostic tests could be destructive or non-destructive in the sense that you age a material over a certain period of time, and after that you perform a test on that material and see whether it passes or fails. If it is a destructive test like tensile strength or electrical breakdown, you will enable catastrophic failure. The difference the difference of this kind of an aging test from ordinary test, material property test is like this. If you are taking a material and you're conducting the breakdown test over when you have that voltage applied for a very long period of time, you have to apply that long period of time. You have to wait that long period of time before failure occurs. In aging, what you do is you simulate the various aging mechanisms, which would be applicable to a system, an insulation under use. So maybe the insulation is operating at 200 degrees centigrade, or there are n number of transient over voltages which are likely on the insulating material. So you quickly subject the insulating material to higher levels of such temperature or transient stresses. Once you have done that, you have kind of speeded up the aging of the material. Now when you perform the dielectric breakdown test, it will break down much faster. So tensile stress also behaves similarly. Then there can also be non-destructive tests. So it is not necessary that the particular stress degrades the material to the extent that you can see a difference in the catastrophic failure, or the catastrophic failure can happen in a short time. So, but there might be some properties which have changed. And for example, the resistance may have changed. Their loss factor may have changed. Partial discharges may occur. So you can perform non-destructive tests like insulation resistance measurements, dissipation factor measurement, partial discharge PD detection to figure out whether, so in that case, the change in insulation resistance, the change in PD levels will give you a measure of the aging. It is these tests or these quantities will then, or these properties will then behave like aging markers. So we will have to set up failure indicators for the diagnostic test that we want to perform. So the methodology is we determine the typical failures for the unaged specimens, then you age the specimen for fixed time intervals, and then apply the diagnostic test. If there is a defined change in the diagnostic, then consider the material to have failed this particular test and you remove it from other aging tests. So this is how you go about the aging tests. There are, of course, certain errors associated with this kind of test. Errors associated are generally because, firstly, you have the phenomena that you're trying to understand is of a statistical nature, and it is limited, and you are performing only a limited number of tests, so you may not get the true picture by a small number of tests. And additionally, you might have error in measurement because of your diagnostic test setup. So the total error will be a sum total of any statistical error and any measurement error. The various IEC recommendations specify the permissible measurement accuracy to be 3%.